Welcome to the demonstration of the project, Effect of Contact Angle of Water Droplets on the Electric Field Distribution of Polymer Insulators. An electrical insulator is also called a power insulator. It is an essential component in the overhead line and transmission line systems. It is usually mounted on the power towers, poles or other structures to prevent the electric current from flowing to the unwanted regions from the overhead conductors. Here's what would happen if the insulators are not present in electrical systems. Polymer insulators are gaining popularity in present due to its hydrophobic nature. We have selected a vertical clamp top insulator with a fiberglass core and silicon housing for the base model of our simulations. Flashover occurs when the arc comes from conductor to tower body, and this is done over the insulator. This occurs due to many things like a failure in one plate of the insulator string, or there is containment on the insulation string which shortens the distance to the tower and flashover occurs. Previous studies has found that water droplets affects the electric field distribution, but no detailed studies have carried out to analyze the effect of contact angle of water droplets, with different pollutants to the distribution of the electric field. Scope of the study carried out was to determine the effect of the contact angle of water droplets on electric field distribution on polymer insulators for dissimilar water conditions and polluted insulator for environmental conditions in Sri Lanka. We have conducted this study for three main scenarios to analyze the E-field distribution on the insulator. The first scenario is to observe the maximum E-field when there are freshwater droplets on the pure silicone rubber and epoxy insulators. The second scenario is for different water droplet condition. Under that, seawater droplets on both types of polymer insulators are considered. In the third scenario, we conducted the analysis to observe the impact of various environmental contaminants. The conclusion is to be taken based on simulation results obtained using the finite element method in ANSYS-Maxwell under defined specifications. The differential techniques that comprise the finite element approach are being used in this software computation method. The insulator model is contained in a cuboidal region where the boundary material is air. The electric field lines are parallel to the faces of the boundary. Modeling the water droplets has done by varying the contact angles ranging from 10 degrees to 170 degrees in the steps of 10 degrees. Water droplet volume is kept constant for all the contact angles. Contact angle of a water droplet can be classified into two types based on the IEC standard, which are dynamic contact angle and status contact angle. Dynamic contact angle is mostly formed in a water droplet that is placed on a slanted surface due to the gravity effect. The static contact angle is formed in a water droplet that is more likely to be placed on a flat surface. Since the weather sheds of the insulator used in this study have flat geometrical shape, only the static contact angle is considered for this project. E-field variations influenced by water droplets under different conditions and industrial contaminants are observed along the observation line, which is the creepage line of the insulator surface. Finally, we have concluded the results based on the observations under three scenarios. Scenario 1: pure silicone rubber and epoxy insulators with freshwater droplets. In here, the variation of maximum electric field doesn't show a distinctive pattern with the contact angle. Based on the comparison, we can say that a pure epoxy insulator having freshwater droplets will undergo lesser E-field stress compared to a pure silicone rubber insulator. Water droplets of moderate contact angles ranging from 70 to 120 degrees will mitigate the electric field stress on the insulator surface. This fact is useful in the designing and manufacturing process of new polymer insulators. Scenario 2: seawater droplets on both silicone rubber and epoxy insulator. Observations shows that at a smaller contact angle of around 10 degrees the maximum E-field is higher. Then it reduces gradually, and at moderate contact angles maximum E-field reaches lower values. Again, at higher contact angles, it shows an increasing trend. However, the trend at moderate contact angles for all cases in this scenario shows a lower E-field intensification and stable values. Hence, for that scenario, moderate contact angles ranging from 80 to 120 degrees are favorable to mitigate electric field stress. Scenario 3: coal ash and cement pollutant layers on the insulator surface. E-field variation in all cases show an increasing trend with contact angles. In the case of coal-contaminated insulators, the maximum E field tends to increase with the contact angle, but the rate of change increase is less than that of the salt contamination due to the high conductivity of salt contaminants than the industrial contaminants. However, the maximum E field obtained for higher contact angles in coastal area pollution is greater than that of the industrial pollution scenario. Thus, insulators in the coastal region are subjected to high E field stresses when there are water droplets of high contact angles present on their surface. The results of the study can be utilized by the manufacturing industry of polymer insulators. In practice, insulators with very high hydrophobicity is preferred in order to avoid water droplets accumulating on the insulator surface. Achieving a high hydrophobicity would be costly. According to this project, the Scenario 3, which represents a more practical situation in the field where insulator is subjected to pollution effect, shows that to mitigate the E field stress along the insulator, the water droplets must be in the moderate contact angles. Here, even though for low contact angles the E field values are minimum, it is not practically recommended because there is a possibility of group of water droplets with lower contact angles forming water films on the insulator. Hence, in the manufacturing process of the insulators, these results can be considered to optimize the model. Introduction of nanoparticles in the mixture to maintain the surface tension of the insulator will be a feasible way to achieve this. This has to be studied and analyzed in detail. Super hydrophobic silicone rubber materials are preferred in the industry owing to their abilities to roll water droplets, self-clean. These super hydrophobic insulators are designed to accommodate water droplets having contact angle more than 150 degrees. But the process of manufacturing super hydrophobic surfaces is complicated and costly, and researches have been carried out to investigate them. Thus, the next best option in the field to mitigate the electric field stresses on polymer insulators is by maintaining hydrophobicity of the insulator, which incorporates optimum contact angle of the water droplet. This project is focused in this manner and objectives are achieved.